Okay, so when dealing with magnetic forces, right, we're going to have four main tenets of what defines the magnetic force and how it reacts to different physical properties. So, similar to the electronic force, which was F equals KQ1, Q2 over R squared, which can be simplified into F equals KQE. Our force depends on a few things, or is proportional to the charge of the particle, which is right here. Whenever the charge of the particle is greater, the force is greater. Same thing for the field strength. If the field strength is greater, charge is greater. Things are beautiful. But this is where magnetic force starts to differ. Instead of just having F equals KQ over E, our force has a velocity term inside of it. So it is directly proportional, or not directly proportional, but it is somewhat dependent on the velocity of the particle. So if the velocity is equal to 0, your force is equal to 0. But if your velocity is greater than 0, then your velocity is going... Realized I marked that down wrong. My bad, I'll fix that right quick. Velocity is greater than 0, it's not going to equal 0. This is going to equal 0. So, if your velocity is greater than 0, your force will not be 0. But if your velocity is 0, then your force will be equal to 0. Best way to say this is there is no force if your particle is not moving. So your particle has to be moving to experience magnetic force. And then the other big complicated bit is right here, is that the force does not align with the magnetic field. The force of the magnetic force is perpendicular to both the velocity and the magnetic field. So if you have velocity A, you have field B, your force will be perpendicular to both of those. This one, it would be coming out of the screen, but I can't draw in 3D, so you're just going to have to deal with it a little bit. Best way to keep track of that is with the right-hand rule. So, with the right-hand rule, if you hold up your right hand and you point your thumb in the direction of the velocity, right? And then you point your finger, your index finger, in the direction of the field, which always goes from north to south. Then your other fingers, when bent at a 90-degree angle, will point in the direction of the force. This only applies for positive particles. If you have a negative particle, then the force will just be flipped. Don't try and use your left hand. It never works out quite the same. I also may have drawn that force wrong, but you get the idea. Now, if your directionality isn't important and you just feel like getting the magnitude of the force, you can use this equation here, where the force is the magnitude of the charge times the velocity times the field magnitude times the sine of the angle between the velocity and the field. So If they are parallel or anti-parallel, which just means equal and opposite, you don't have any field or any force. But if they're at 90 degrees, then you're going to get the full force. Since sine at 90 is 1 and sine at 180 or 0 is 0. So what units do we use for the field strength? So we know a few things. We know A, our field equation, that our F is equal to Q. Sorry, we're going to use this one. It's easier for the units. Q, V, B, sine theta, right? F is in terms of newtons. Velocity is in terms of meters per second. Q is in terms of coulombs. So we're going to try and find the units of B. If we use this equation, QVB sine theta, we're left with B equals F over QV sine theta, or sine phi, my bad. The sine phi is unitless. We're going to be left with F over QV, which is newtons per coulombs per meter second. That deal. Coulombs per second is the same as an amp. So newtons per amp meters, which is a lot of words to say, so they came up with T, or Tesla, to rate the magnitude of the vector of a magnetic field. You do have to put a direction in there if you want people to understand what the direction of that field is. So now it's time for a little practice problem. If we have a proton gun, an Acme proton gun, and a field going into the negative y of magnitude b and direction in the b vector, we have a proton that got shot out of our Acme proton gun with a velocity v0 in the positive x direction. What is our force going to be? I chose some arbitrary values for the velocity and some arbitrary values for the field strength, but that actually is the charge of a proton. So we know that F is Q times the cross product of V and B. So we plugged in our Q. And for the cross product of V and B, you can take the scalars off of your numbers, keep them outside of the cross product, and then just do the cross product of your vectors. So we'll put those in there, reduce some terms, and complete our cross product, which will leave us with our final answer of 9.6 times 10 to the negative 14 newtons in the negative z direction, which you can verify real quickly. If you have B pointing down and your velocity pointing this way, and you put your thumb in the velocity and your finger pointing towards the field or aligned with the field, your other fingers will be able to point in the direction of negative z. All right, and then magnetic flux. It is almost exactly the same as electric flux. In fact, it is exactly the same as magnetic flux. The only thing that differs a little bit is the units, which I'm not 100% sure if we're going to be using in this class, but either way, the unit here is the Weber. So WB, big W, little b, is the unit for a Weber, which is lowercase w. He was famous enough to get his name lowercased. Very fun, very cool. Not even Newton could do that. As I was saying, there was a bit of a notation error there. The flux of EDA is equal to phi. The flux of BDA is equal to phi B. If you're doing it over a closed surface, it's equal to 0. Same thing for magnetic flux, which is equal to 0. And if everything stays consistent, your field is all parallel, your normal vectors are all consistent, then you can say that you can skip the integrals. And you can just do B, magnitude of B, magnitude of A, and the cosine of phi, which is the angle between them, which the angle between the normal vector and the field vector. So here's a bit of a practice problem. The field strength, what field strength is required to keep a single proton in orbit around the radius r? If we are given the initial velocity and we are given the charge, right? And we're given the radius, we need to find F that will sustain that orbit, and thus we'll find B, which will produce F. So, things we know. We know that F is equal to the magnitude of Q times V times B times the sine of phi, which is the angle between V and B, right? And we can choose what angle B goes in, so we'll choose for it to be 90, since that makes math a whole ton easier. So that can either mean that it's pointing directly into the screen, or it can mean that it's pointing directly out of the screen. Either way, another thing we know is that F for centripetal force is equal to the mass of the particle, or mass of the thing, times velocity squared over the radius of the orbit, right? So we can set those equations equal to each other, since those forces would have to be equal for this to be in a perpetual orbit. And we can simplify by deleting one of those v terms and moving r over to the right side, which gives us that equation. So now we can plug in our known, our given. So Q is this, V is this, M is that, our radius, 1 meter, made it simple. There's no cross products, there's no integration, just plug and chug, and you get a 3.13 times 10 to the negative 2 Tesla, which is a pretty strong magnet to keep a 1 proton moving at 1/100th of the speed of light in orbit. Pretty fun, pretty cool. So putting it all together, we know that the electric field, electric force equation is F equals Q times E. We know that for magnets now, force is equal to the magnitude of Q times the cross product of V and B. So, what can we learn from this? We can learn that electromagnetism, due to the superposition of vectors, which means that if you have two vectors acting at the same time, you can just add them up, put them tip to tail, and get a resultant vector, F. So we can do force is just the electroforce and the magnetism force, and you get the equation for electromagnetism. Some fancy guy came up with this. It's called the Lorentz force equation. This one right here. This one's a bit simplified if you want to take the Q out and you just want to mess with the E's and the VB's. That one's up to you. You can mess around with this equation all you want, hence the yada yada. But nonetheless, this is our final equation for the forces determined by electric field and magnetic field.